Hello and welcome back to my YouTube channel or the Big Structural Hub. This is the #1 channel for structural insight and a place where you learn, build, and innovate. Today I want to do example number 2, and this is T-beam design, and it is a simply supported beam. I'm only going to work on bending and shear. Then tomorrow I will conclude by bending and reinforcement detailing, and then that will mark the end of this simply supported beam design. And as from next week, we will start continuous beam design. So without wasting any time, the question is on the board and it reads, figure below shows a plain view of a slab casted monolithically with beam. Design and detail beam marked X using the following information. Number 1, we have the variable action is equal to 5 kilonewton per meter square. Unit weight of concrete is equal to 24 kilonewton per meter cubic. The overall depth of the beam is equal to 550 millimeter, and the thickness of slab is equal to 150 millimeter. Assume class XC1 exposure. Then number 6, grade of 500 steel. Number 7, the beam is made of class C2530 concrete. And then the breadth of rib is 250 millimeter. And then you have the finishes, 1 kilonewton per meter square. Then of course assume any other relevant information. So this is the plan, as you can see, and this is beam X. It is a center beam, and as you can see, these are the slabs, and this slab is spaced at 5 meter center to center, and then the span of this beam is 7 meter. So let's see how we can tackle or we can design this beam X. So this is beam X, like that. So solution, as you can see, this beam X is a center beam, and therefore it is supporting this slab and this slab, and we cannot say it is supporting a half of this slab and a half of this slab. So what you are supposed to do, we are supposed to determine whether this slab is a one-way spanning slab or a two-way spanning slab. This is because for a two-way spanning slab, the load is distributed at 45 degrees. So let's determine whether it is a two-way or a one-way spanning slab. So to determine, you need to calculate the ratio of Ly over Lx, whereby Ly is the longer span, which is 7 meters, and Lx is the shorter span, which is 5 meters. So this one is equal to 7 divided by 5, 1.4. So this is 1.4, which is less than 2. Therefore, two-way spanning slab. So for such a case, the load at this slab and this slab is distributed at 45 degrees. So let's draw the load distribution paths. So this is 45. And also this, like that. And here, we also have 45. This is 45 degrees and also 45 degrees. Like that. It will also be the same to this side. So 45, 45. This is 45. This is 45, as well as here. Like that. So this beam is supporting this area, this shaded area. Like that. So for us to design this beam, we will consider this area. We will consider this area. So let's first calculate the area of this shaded part. As you can see, this is 45 degree, as well as this. Also this one, 45. So let's calculate this distance from here. This distance x. We know that from here, this is the center of this side. So from here up to here is 2.5. Also here 2.5. So if this is 45 degree, like that, if we can draw it here, so this is 45, this is x, and this is 2.5. Therefore x is equal to tan 45 degree times 2.5. So tan 45 is 1 times 2.5 is equal to 2.5. So it means from here to here is 2.5. As well from here up to this point is 2.5. So we need this distance from here to here. So you'll take 2.5 plus 2.5, which is 5. Then you subtract from 7. So you will get 2. So this is 2 meters. So from this diagram, so from here is 7 meters. And then here is 2 meters. And then this height, the height, (2.5). You can calculate the area of this shape, which is a half A plus B H, then times 2, because they are 2 in number, this one and this one. So this one is equal to a half into bracket 2 plus 7 times 2.5 times 2. So the answer is 2 plus 7 times 0.5 times 2.5 times 2. So this is 22.5. This is 22.5 meter square. So it means this beam is supporting its own weight plus the weight of this slab, which has an area of 22.5 meter square. So let's proceed. And since we have already utilized this as a plan, I can clean here so that you can continue. But something very important at this at this side is 22.5 meters square, which is the area of this shaded region. So write it somewhere. We now proceed to loading. And loading will start by the permanent action, which is GK. And under GK, we have the weight of the slab. So weight of the slab. So remember the thickness of the slab is 150. So this is 150. Convert this 150 into meters. So divided by 1,000 times the area of the slab is 22.5 meter cubic, and then times the density. Density is 24. Then you divide everything by 7, like that. Let me show you the conversion. So here, 150 divided by 1,000 is meter. We have changed millimeter to meter, and then times 22.5 is meter square, not cubic, meter square, times 24 is kilonewton per meter cubic. Therefore, this will cancel with this and this. So we will remain with kilonewton. And to make it a UDL, a uniformly distributed load, you divide it by the span, which is 7. So let's carry out the operation. This is 150. So this is 11.57. So this one is equal to 11.57 kilonewton per meter. We proceed to beam, on weight of the beam. On weight of the beam. So for the beam, allow me to draw the flange section of this beam. So if this is the beam, and this is the thickness of the slab, which is 150 millimeter, and the overall H is 550. Then the depth of the slab will be 550 minus 150, which is 400 millimeter. So we'll use this 400 to calculate the on weight of the beam. Again, take 400, convert it to meters all over 1,000 times the breadth of the beam is equal to 250 millimeters. Here it is. The breadth of the rib times 250 all over 1,000. Then times the unit weight of this concrete, 24. So this one will give us, so for this one you don't divide by 7 because this is meters times kilonewton per meter cubic. So here, then meter. So no need to divide it by 7. So we have 0.4 times 0.25 times 24. So this is 2.4 kilonewton per meter. So this is the on weight of the beam. We proceed to finishes. Finishes is part of the permanent action. So finishes is equal to 1 kilonewton per meter square. So this one, you will multiply it by the area, because this finishes will be done on the slab, and the area of the slab is 22.5. So times 22.5 meter square, and then you divide everything by 7, because meter will count with meter, so you remain with kilonewton. And to make this loading UDL, divide it by the span. So this one is equal to 22.5 divided by 7, 3.21 kilonewton per meter. Of course, we are supposed to calculate the total permanent action. So total GK is equal to 11.57 plus 2.4 plus 3.21. This one is equal to 11.57 plus 2.4 plus 3.21. So this is 17.18. 17.18 kilonewton per meter. Remember, you also have QK. This is the variable action, or the imposed or live load. So QK, you have been given as 5 kilonewton per meter square. 5 kilonewton per meter square. So this one, you will multiply it by the area, which is 22.5, and then divide it by 7, so that you can have your loading in UDL. So this is 5 times 22.5 divided by 7. So 16.07 kilonewton per meter. Then the design ultimate load, which is W, is equal to 1.35 GK plus 1.5 QK. So this one is equal to 1.35 times 17.18 plus 1.5 times 16.07. So this one is equal to 1.35 times 17.18 plus 1.5 times 16.07. So this is 47.3 kilonewton per meter. So this is the design ultimate load, which is W. Allow me to clean here, but write this somewhere, because we are going to use it. Design ultimate moment. So if this is our beam, and the loading is 47.3 kilonewton per meter, and then the span is 7 meters, then M ED is equal to W L square all over 8. So this one is equal to 47.3 times 7 square all over 8. So this one will give us 47.3 times 7 square divided by 8. So this is 289.71 kilonewton meter. So MAD is equal to 289.71 kilonewton meter. That is our MAD. After here, we now proceed to the calculation of D. We proceed to calculation of D. But before we start the calculation of D, let's first calculate the nominal cover. So for the nominal cover, we have been told to use class XC1 exposure. So in Eurocode 1, C minimum is given by the following: the maximum of, we have C minimum durability, we have C minimum B, and 10 millimeters. So minimum cover to reinforcement durability is given in table 8.10. 8.10, and for our case is equal to C is equal to 15 millimeter. I will show you the table. I show you the table after this explanation. And then you will say, assume diameter of longitudinal bar is equal to 25 millimeters. Assume the diameter of longitudinal reinforcement of a bar is equal to 25 millimeter. Hence, C minimum B is from this diameter of the bar, which is 25 millimeters. So, if you compare these three, C minimum durability is 15, this is 25 and 10. Which one is the maximum? Is 25 millimeter. Therefore, hence, nominal cover, to main steel is equal to C plus deviation in concrete cover, which is 10 millimeters. So this one is equal to 25 plus 10, which is equal to 35 millimeter. Remember, this 35 is to main steel. Then we will say, assuming you will say again, assuming the diameter of link. So assume diameter of link is equal to 8 millimeter, like that. So nominal cover to link is equal to 35 minus 8, which is equal to 27 millimeter, and this 27 is greater than nominal cover for durability, which is 15. So 27 is greater than nominal cover to durability, which is 15 plus 10. So this one is equal to 25 millimeters. So we'll adapt 27. Therefore, our cover is equal to 27 millimeters. So is equal to 27. So we are going to use this 27 millimeters in our calculation. So this is table 8.10, minimum cover to reinforcement for durability, see minimum durability. So we go to our class, that is class XC1. So you can see it is 15. So that is how you read that table. Now let's calculate the effective depth, which is D. So D, it is given by this formula, H minus cover minus diameter of link minus a half diameter of main bar. So this one is equal to D is equal to H is 550, cover is 27, minus diameter of link, this is 8, 25 over 2. This is the diameter of the main bar, which is equal to 550 minus 27 minus 8 minus 25 over 2. So this is 500 or 2.5. So let's make it 5 or 2 millimeters. So after this, we proceed to effective flange width, which is B, like that. So the formula for this is plus BW, whereby is equal to 0.2 plus and it must be less or equal to 0.2, like that. So this is the formula, whereby 1 times length. So this one is equal to 1 times 7, which is equal to 7 meters. And remember, this is our section. So this from here to here is 5 meters. From here to here is 5 meters. And then from here, this one is 250 millimeters. I will explain why this is 5 meters. So you remember in our design, we had our beam, which was X, or which is X. So this is beam X, and it is supporting so this beam is supporting this loading on the slab. So here, from here up to this point, this is where we have our flange, and here so that is it, such that this distance from here to here is a half of the one we were given in our plan, which is 5, 5. So 5 on this side, 5 on this side. So here is 2.5, here is 2.5. Therefore, if you add 2.5, 2.5, you'll get 5. So you get 5 meters flange. So we continue. So 0.2, or you calculate direct, so B is equal to 0.2. B1 is this distance divided by 2. Is distance X. So you take 5,000 minus 250, you divide by 2, then plus 0.1 times 7,000, which must be less or equal to 0.2 times 7,000. So this one is equal to 1175 millimeter. So it must be less than 0.2 times 7,000. So this is 1400. Therefore, K. So if our BFF1 is equal to 1175 millimeter, therefore, also B is equal to 1175 millimeter. Therefore, B is equal to summation, which is 1175 plus 1175 plus 250, which is the breadth of the web. So this one will give us 1175 times 2 plus 250. So this is 2600 millimeters. This is 2600 millimeters. So we now proceed to K. So K prime is equal to 0.167. Therefore K is equal to MED all over FCK BD FCK BEFF D square. So this one is equal to MED. Let me check for MED. MED is equal to 287.71. 289.71 multiplied by 10 to power of 6 to change it from kilonewton meter to newton millimeter all over FCK. This is the strength of concrete, which is 25, times 2600 times D, which is 502 square. So this is 289.7 times 10 to power of 6. 25 times 2600 times 502 square. So this is 0.018. So 0.018 is less than 0.167. In other words, K is less than K prime. Therefore, no compression. Reinforcement is needed. So we design as a single beam. So allow me to clean everything on the board so that you can continue. Now calculate the neutral axis, which is x. X is equal to D minus Z over 0.4, whereby Z is equal to so this is the formula that will help you to obtain Z. So Z is equal to D is 502, 0.5 plus 0.25 minus 3, K is 0.018 over 3.4. Like that. So let's carry out the operation. This is 0.25. minus 3 times 0.018 all over 3.4 raised to power 0.5 plus 0.5. So this is 0.98 times 502. And remember, Z is limited to, it must be less or equal to 0.95D. It therefore implies this value is greater than this. So we will adapt 0.95D. Therefore, Z is equal to 0.95D, which is equal to 0.95 times 502, which is equal to 0.95 times 502. 476.9 millimeters. So this is Z. Therefore, X is equal to 502 minus 476.9 all over 0.4. So this one is equal to 502 minus answer divided by 0.4. So this is 62.75 millimeter or 63. It therefore imply X is less than HF, which is 150 millimeter. So design as a rectangular beam. But if X was greater than HF, then we could have designed as a true T-beam. So A of steel is equal to MED all over 0.87 F Y K Z. So this one is equal to our MED. Let me check for MED. 289.71 times 10 to the power of 6 multiply by 10 to the power of 6 to change it from kilonewton meter to Newton millimeter all over 0.87 times FYK is 500 times Z 476.9. So area of steel is equal to 289.71 times 10 to the power of 6 divided by 0.87 times 500 times 476.9. So this is 1397 millimeter square. So this is the area of tension reinforcement. Then you will say from table 3.10. I hope you know how to convert this area into steel reinforcement. Provide 3H 25 and then the area of steel is equal to 1470 millimeter square. And then after this we check the reinforcement percentages. So we have AS mean, which is equal to 0.26 FCTM over FYK BWD. So this one is equal to 0.26 times FCTM is given by this formula 0.3, FCK, which is 25 raised to power 2 over 3 all over 500, then times 250, which is BW, times D. D is 502, like that. So this one is equal to, let's carry out the operation, 0.26 times 0.3 times 25 over 2 over 3 times 250 times 502 divided by 500. So this is 167 millimeter square. So I have said that FCTM, this one is given by this formula 0.3 FCK raised to power 2 over 3, like that. And then we will proceed to 0.0013 BTW. So this one is equal to 0.0013 times 250 times W this one is BTD. No, it's BWD. It is BWD, which is 250 times 5 or 2. So this one is equal to 0.0013 times 250 times 5 or 2. 163 millimeter square. We now proceed to 0.04 AC. So this one is 0.04. AC is the area of the section of the slab. Section is 400 by 250. So this one is equal to 0.04 times 400 times 250. So this is 4,000. This is 4,000 millimeter square. It therefore means 0.04 AC, it must be greater or equal to area of steel, and this one must be greater or equal to AS mean or 0.26 FCTM FYK BWD, which must be greater or equal to 0.0013 BWD. So as you can see, everything satisfies this equation. Therefore, okay. Therefore, okay. Allow me to clean here and here so that you can continue. Now come to clear distances or minimum spacing. So if this is our beam, so the clear distance is the distance between these two bars and these two bars. So this distance is 250. So to calculate the clear distance, you will take 250 minus 2 times cover, which is 27. So here you subtract this cover and then this cover, then minus the diameters of these three bars. So this is 3 times the bar is 25, and then divided by the number of spaces. Number of spaces, we have 1, 2, which is 3 minus 1. So this one will give us, let's do the operation. 250 minus 54 minus 75 divided by 2, 60.5. So this is 60.5 millimeters. So this will be the distance between the bars. Therefore, 60.5 millimeters, it must be greater minimum of the aggregate, which is DG plus 5, and then we have bar diameter, and then we have 20 millimeter. So if we assume the size of aggregate is 20, then plus 5, this will be 25 millimeters. The bar diameter is 25 millimeters, and then 20 millimeters. So as you can see, 60.5 is greater than 20 millimeters. Therefore, okay, like that. We now proceed to shear reinforcement. So VED is the design shear force, which is given by WL all over 2. So this one is equal to 47.3 times 7 all over 2. So this one is equal to 165.55 kilonewton. And VRDC, which is the shear resistance of concrete without reinforcement, is given by whereby VRDC must be greater or equal to like that. So let's now break this down and calculate each value for each formula in the bracket. So we have CRDC this one is equal to 0.18 over partial safety factor 1.5, which is equal to 0.12 Newton per millimeter square. We have K. K is equal to 1 plus 200 all over D raised power a half. So this one is equal to 1 plus 200 all over 5 or 2 raised power 0.5, which is equal to 1.63, and it is less than, it must be less than or equal to 2.0, therefore K. So this one is given, which is the reinforcement ratio ASL over BWD, and it must be less than 0.02. So this is the area we calculated, which is 1397 over 250 times 502. You will get 0.011, which is less than 0.02, which is okay. And then this one is the axial. No, this is the average compressive stress due to axial load. But since there is no axial load, this one will be equal to 0. So if we insert everything in our formula, we will get 74.09 kilonewton, and then V mean BWD. So remember, if this is 0, then it means this one K, here K, because this is K, this one will equal to 0. Therefore, we will remain only with V mean. So this one is equal to 0. 0. So 0 times K is 0. So we will remain with V mean BWD. And V mean is given by this formula, 0.035 K raised to power 3 over 2, FCK raised to power half. Then BWD is this one. So if we insert everything this formula, we will get 45 kilonewton. Remember to multiply by 10 to power negative 3 to change it from Newton to kilonewton. So as you can see, 74.09 is greater than 45 kilonewton, which is V mean BWD, which is okay. Since VR is less than VED, shear reinforcement must be provided. Shear reinforcement must be provided. Now let's calculate the VRD max. This is the check compression capacity of compression strut. which is VRD max, assuming (21.8°). So VRD max is given by this formula. So V is equal to 0.6 into bracket 1 minus FCK over 250. So for FCK less than 50 megapascals or 50 Newton per millimeter square. So this one is equal to 0.6, 1 minus 25 over 250. So it's equal to 0.54. And then FCD is equal to alpha CC FCK over partial factor of safety. So this one is equal to 0.85 times 25 over 1.5. So this one is equal to 14.16. And then Z is equal to 0.9D, which is equal to 0.9 times 502, which is equal to 0.9 times 502, 0.9 times 502. So this is 451.8. 451.8. Like that. So VRD max, we can now insert these values in the formula. So VRD max is equal to, and remember cot 21.8 degree is equal to 2.5, and the tan 21.8 is equal to 0.4. Cot is cosine over sine. So you can do cosine 21.8 all over sine 21.8. You'll get 2.5. VRD max is equal to, let's insert these values in our formulas. So BW is 250 times Z is 451.8 times V 0.54 all over times FCD. FCD is 14.16 all over 2.5 plus 0.4. Remember to multiply everything by 10 to the power of -3 so that you can have your answer in kilonewton. So let's carry out the operation. So you have 250 times 451.8 times 0.54 times 14.16 divided by 2.5 plus 0.4, then times 10 to the power of negative 3. So this is 297. So this one is equal to 297.81 kilonewtons. So this is VRD max. VRD max, which is equal to 297.81 kilonewton. Therefore, this one is greater than VED, which is 165.55. 165.55 kilonewton. Therefore, K. Therefore, okay. We now proceed to diameter and the spacing of links. Diameter and spacing of links. So VED is VED must be less or equal to VRD max, and VRDS is equal to ASW over S Z FYWD cot theta. Cot theta. This is the shear reinforcement resistance. Shear reinforcement resistance. Therefore, for us to get VRDS, we will assume two legged stirrups of diameter 8 millimeters. Therefore, ASW is the area of these assumed stirrups. So this will be 2 times pi times d, which is 8 square all over 4. So this one is equal to 32 pi. And then we assume S, which is spacing, to be 300 millimeter center to center. Then Z is equal to 0.9 D, which is equal to 0.9 times 502. So this one is equal to 451.8 millimeters. Cot theta is equal to 2.5, or you can do it with your calculator. That is cos 21.8 over sine 21.8. You'll get 2.5. And then, is there anything you are missing? FYD. FYWD is equal to 500 over 1.15. So the formula is FYK all over partial safety factor for steel. So VRDS is equal to, let's put everything in the formula. ASW is 32 pi. All over spacing is 300 times Z is 451.8 then times FYWD is 500 or 1.15, then times 2.5 times 2.5 times 10 to the power of -3, so that you can change it from Newton to kilonewton. So let's carry out the operation. So this is 32 pi over 300 times 451.8 times 500 over 1.15 times 25, times 2.5 times 10 to the power of -3. So this is 165. This is 165. 165 kilonewton. So this is VRDS. So if you can sketch here, so this is 47.30 kilonewton per meter. The beam is spanning 7 meters. Let's draw the shear force diagram. So this is VED, which is equal to 165.55 kilonewton. The same as to this, 165.55 kilonewton. And here, and also here, so these two is what we call VRDS with minimum links. With minimum links. Like that. So it means you can calculate this distance as well as this. Let's call it x because they are the same. So from here, this is 3.5, a half of 7. Also this one is 3.5. So to calculate this distance, take this loading up to this point. So this is the loading. So take here, VRDC here is 165 kilonewton. Therefore, the loading on the beam will begin by this 165 minus, because the loading is in the downward direction, minus 47.3 times x is equal to 0. 0 because here the shear force is 0, which imply x is equal to, divide 165 by 47.3. So x is equal to, let me do it, 165 divided by 47.3, 3.49. X is equal to 3.49. 3.49 meters. So this is 3.49 meters. So this 3.49 meters, 3.49, you'll provide minimum links. So then the remaining distance, you take 3.5 minus 3.49, which is 0.01, as well as this one, 0.01. So here you will provide at distance x, will provide minimum reinforcement. So you will say that where VED, where VAD is less than VRDC, provide minimum shear reinforcement, provide minimum shear reinforcement. According to is equal to AS SBW sin alpha, and it must be greater than the reinforcement minimum. So AS, so ignore this sign and make it an equal sign, such that AS over SPW sin alpha is equal to reinforcement area or reinforcement minimum. Then make AS over S the subject of the formula. So this one is equal to that. So alpha is equal to 90. So sine 90 is equal to 1. And this one is given by this formula, 0.08 FCK raised power 0.5 or a half over FYK. So this one is equal to 0.08 FCK is 25 raised power 0.5 over 500. So this one is equal to 800 times 10 to the power of negative 6. To the power of negative 6. We are concluding. So AS W over S is equal to 800 times 10 to the power of negative 6 times 250 times 1. So this one is equal to 0.2. 0.2. Hence, from table, (3.13) provide H8 at 300 millimeter center to center. I hope you know how to read this or to convert this to a bar and a spacing. 300 millimeter center to center. Then from the table, ASW over S is equal to 0.335. And then the maximum spacing is equal to 0.75 D. So this is 0.75 times 502. So this one is equal to 376.5 millimeter, which is okay because here is 300 millimeter center to center here. So let's check if this will be enough to resist the shear on this beam. So let's confirm. So we know that VRDS is equal to ASW over SZ FYWD cot theta. But here, this one we already have it as 0.335. So just do the replacement. So this is 0.335 times Z. Z is 0.9 times 502 times FYWD is 500 over 1.15 times cot theta is 2.5, then times 10 to the power of negative 3. So let's check. So 0.335 times 0.9 times 502 times 500 all over 1.15 times 2.5 times 10 to the power of negative 3. So this one is equal to 165. 165. So this one we will provide H8 at 300 millimeters center to center. Therefore, the final statement will say that the final statement for shear reinforcement, you will say that provide two legged H8 at 300 millimeter center to center for the entire beam. And that marks the end of our today's session. As I told you, I was only to do bending and shear. Then I will conclude either tomorrow or the following day by deflection and reinforcement detailment. So for those who have not subscribed to the channel, please subscribe. Don't just be a silent followers. Subscribe and be a member. If you have any question, just comment. You can also share the videos. You can also like. So let's help this channel to grow. So that is for today, and let's meet in my next session. And thank you.